Hello and welcome to AUTOINFORM Online Magazine Diagnostic Workshop. My name is Frank Massey and today I'd like to take a look at a particular issue of interpretation of data. By that I mean, how do we begin a process of repair when a vehicle has a fault? It's certainly true to say you should begin with a serial diagnostic evaluation, but how do we react to the information that particular tool then provides us with? I'm tempted to say that the diagnostic approach using serial communication is an invitation to speculate only. And by that, with the greatest respect, I mean that those faults stored in the computer can be caused by a whole series of events which do not directly relate to the cause of the problem. In other words, what I'm saying is you may be looking at symptoms, not cause. This particular vehicle is a Rover 75 diesel 2 litre on Bosch DD4 control. The vehicle is a genuine repair situation brought into our business with the symptoms of intermittent failure to start. Now with diesel, there can be many reasons why those symptoms can bring about a no start condition. I have conducted a serial evaluation, the results of which I have in front of me. I'm going to go through those in a methodical, logical approach, looking not at the symptoms but at potential cause. Led by those causes or potential causes, I've attached some equipment already because we're going to evaluate the system in two respects: hydraulically using a priming gauge and electronically using an oscilloscope. So the first thing I'd like to do is just review the equipment we're using and then go through the symptoms as previously described with the serial communication extraction that we've already achieved. I've attached the low pressure priming gauge, and we've certainly used this gauge many times before. The advantages of this gauge are that we take direct pressure measurement. In our case, this particular system uses a positive supply system. In other words, there is a positive supply electric pump fitted to the vehicle which provides positive priming pressure to the high pressure common rail pump. So we can read directly off the gauge positive pressure. We also have the ability to look at the fuel flow in the form of a sight block, giving free and easy access to see if there's any cavitation, pockets of air, bubbles, or indeed any contamination. So that has already been set up. We'll almost certainly examine that to begin with. Now, of course, this vehicle has an intermittent fault. The problem with intermittent faults are, of course, that the fault may not be present whilst the test is being conducted. Our view of that is you have to review the status of the vehicle only when the fault is present. So we may have to conduct these tests several times. So far, this vehicle has not failed us, and I don't anticipate the failure to happen on camera, but at least the process can be discussed and demonstrated quite clearly. So priming pressure is one of the things that we're examining. We're then going to take a look at rail pressure interpreted electronically by interpreting the voltage path from the rail pressure sensor. We're also going to be measuring current through the injectors using a Hall effect inductive clamp to evaluate how the injectors are being driven electronically, and as a result of that we should then quite easily be able to determine what the cause of this problem is with a no start condition. But first of all, I'd like to go to review the serial data we've extracted, then perhaps describe really how my mind is being driven to approach this particular challenge. One of the problems with serial communication data is that you have no idea initially how these faults have been stored. Are they man-made? Have components been disconnected? Are they genuine? And the difficulty there is we need to take them into account but not take account of them. Now the faults are pre-pressure control, P1260. Now pre-pressure control is priming. So do we have a priming problem? I don't know. How can we rely on the DTC? Well, we can't. because the DTC is driven or created when the low pressure sensor mounted on the fuel filter housing reports a voltage out of specification. It could be a sensor fault, it could be a wiring fault to the sensor, it could actually be a priming problem. We just don't know. Our view is the end product of priming is a hydraulic function, and the hydraulic function is pressure and flow. We go for the final function. I have at this moment in time no interest in that pressure sensor. I want to know what's happening hydraulically in the system. That's the first DTC. There's a DTC relating to the cooling fan, of which I have no interest with. It will not give me a no start condition. We have a P1E45 status intermittent. All of these, by the way, are intermittent. Capacitor 1 voltage, booster voltage too low. Now what that rather complex, overpowering statement is trying to explain is that the capacitor which drives the injectors, the operation coil with here, is power driven by discharging a capacitor. The capacitor is mounted in the ECU. If that capacitor fails in any way, the injector will not be opened and therefore the vehicle will not run. So it would satisfy the conditions which we are expecting a no-run condition. So that is one possibility. But I don't know if that capacitor voltage is a man-made DTC, has somebody disconnected the injector and it's installed that particular fault. On this particular system, if that single capacitor fails or one injector were to fail, the vehicle will not run. It uses the closing event of the injector to partially charge the capacitor for the next injected event. So if an injector were to fail or the capacitor were to fail, this vehicle will not run. It will not start and or will cut out when in operation. So that is an issue we need to resolve. To do that, we're going to measure current. The capacitor voltage is monitored serially and is displayed as a voltage. Now the rule is voltage up, current down, voltage up. When we switch an injector off, the voltage diminishes, the current diminishes, the voltage increases. The back EMF, which is displayed on the scan tool as capacitor voltage, is in effect an interpretation of the current path and the quality and quantity of the current path through the injector. We're going to measure this as current. End product, more reliable, much more accurate. We're going to measure current flow through that circuit. The next fault, P1190, intermittent, rail pressure plausibility, control deviation too large. Another huge mouthful. The number of potential causes in that are enormous. 3 phases of common rail, storage and priming, pressure generation, fuel delivery. We potentially have a problem with pressure generation, deviation rail pressure. What that means is that the DRV, Druck Regulation Ventricle, it's a pressure control device. It controls the escape of fuel back to the tank. So by restricting the escape passage or spill passage, pressure will increase. So you will increase pressure by driving this device in. You will release pressure by allowing the device to open more freely. So you apply more current to this to drive it in, pressure increase, remove current out to reduce the pressure in the rail. This is controlled by duty, and that's controlled by the ECU, and we're going to monitor the duty on that valve electronically. It can also be monitored serially. The pump on this vehicle is a Bosch CP1, 3-piston pump with the DRV mounted on the back of the pump. So the actual escape route back to the tank is controlled by the DRV directly mounted on the pump. In some cases, that device on the back of the fuel rail or the accumulator. So potentially it could be mounted in that type of position, not in our case. In our case we have a blind rail, which is what this one is, with a CP1 pump. The deviation that the diagnostic code refers to is a deviation in the output voltage from the rail pressure sensor with regard to the duty cycle of this valve. The two are monitored in closed loop very closely. So when a deviation in voltage is seen, it will compare the control duty. And what should happen is that the correct voltage should be achieved with the correct duty command to this valve. And we're going to monitor that. Where that's important is that we can achieve the right voltage in the rail, therefore the right hydraulic pressure, at the expense of the incorrect duty. In other words, the pump may have to work harder than it should to create the pressure, potentially a leak or poor priming, or it could be the pressure's too high. The valve is mechanically sticking, or perhaps the escape route in some way is blocked, preventing escape of the diesel fuel, in which case the duty will be reduced. And that is not acceptable, so we need to monitor those two functions. But I think first of all, let's take a look at priming. Storage and priming, pressure generation, fuel delivery. In the correct order, given the faults that we have, always make sure priming is correct before attempting to blame the high pressure pump or potential leakage across the injectors. At the moment, we don't know where the fault is, but we're going to establish, or the method we're going to establish as to direct us to the cause, not the symptoms. What we're looking at here are symptoms. So the first port of call is priming pressure. As I've explained, this variation of system, some vehicles have a pump in the tank and an intermediate pump, in effect supplying positive pressure to the high pressure pump, and we can monitor this. We're actually monitoring it after the fuel filter, before the high pressure pump. We're measuring it in real time, actual hydraulic pressure. So the first thing we need to do now is simply, in fact, this particular system will prime simply by turning the key on and will provide the right pressure. We don't actually need to run the vehicle, although we do have the ability with this gauge. This gauge has self-sealing couplings so that we can extend these hoses into the vehicle if need be and drive the vehicle on the road, actually monitoring real-time hydraulic events. In our case, for the moment, we're doing it in the workshop. So first of all, what I'd like to do is just do a static key-on test to have a look at the actual priming pressure. Now, I've got an assistant who's going to help me just with the various tests we're doing with starting and running the vehicle. But for now, if you can kindly just turn the ignition on for me. A static test. So we've got 2.6, 2.8, 3 bar of pressure. It's holding good. Now, of course, intermittent faults, any time at all, the pump could cut out. There could be an issue with this hydraulic pressure. At the moment, there isn't. The pressure came up promptly. It's holding steady. There is no cavitation whatsoever within that sight block. And I have to say, at the moment, I have no problems with that. If I did have a problem, if you can turn off, please. If I did have a problem with that pressure, the next course of action would then be to check the current flow through the pump, because I then want to prove, is this a problem with the pump or the actual hydraulic circuit, in other words, the pipework, block filter or whatever. And by monitoring current flow through the pump, that also helps me predict whether it's a pump fault or not. But at the moment, I can't fault it, so there's no point in me doing any checks with regards to current through the pump. So that part of the test for now is finished. I'm leaving the gauge attached, so I keep my eye on that at all times and we're doing other further testing. But apart from that, that test is finished. One of the other DTCs I mentioned was rail pressure deviation. Now, the rail pressure sensor is a 5 volts device, 3 wires, output, power, ground. In most cases, not in all, but in most cases, the middle pin is the output. I've connected a probe, a acupuncture probe, into the middle pin. It's a 5 volt device. It is fed with 5 volts, has a ground reference through the ECU, and its return circuit will then report the theoretical hydraulic pressure against voltage. There is what we call a plausibility value of 0.5 of a volt, key on 0.5. So we're going to go through a series of tests now whereby we turn the key on static. We're going to look for 0.5. We're going to crank the vehicle and observe the pressure rise against voltage, or I should say voltage against pressure rise. We're then going to allow the vehicle to idle for a short period of time to look at stability, because deviation means that the pressure against voltage is wrong, and that could be a sticking DRV. Deviation, it's mechanically sticking, because the pressure sensor and the DRV work very closely in closed loop. They are each monitored very, very carefully. Then we're going to open the throttle wide open, do a simulated high pressure test, back to natural idle and key off. And that profile test, as we call it, then will give us an awful lot of information about the functionality of priming, pressure generation, and to a point fuel delivery, which is the job of the injector. Finally, when we've done that, we're then going to attach the current device onto just one injector. We will of course test all 4 injectors, but initially, just for the purpose of the filming, to one injector and monitor the actual current flow through the control solenoid. So what I'd like to do first of all is set the scope up before we start the vehicle or anything. The first channel, we'll check where we're connected. The blue channel is connected to the DRV. So my blue probe is connected to the control circuit. This is a ground control device, which means it's ground switched on. On means in means higher pressure. So the higher the duty, the more the pressure. I'm monitoring that duty with the scope on channel 1. Now, all devices which use movement as a function will use nominal battery voltage, so I need a 0 to 20 volt range. I've already set the range. You can see I have an infinite adjustment of range. 20 volt range has been set on channel 1. Channel 2, red, is on the middle pin of the rail pressure sensor. Voltage, and it's a 5 volt device, so I've set a 5 volt range. Current, I've not yet set up. Now we use voltage for current, it's quicker and more practical. We turn the Hall effect inductive clamp on to a 20 amp range. These injectors will use about 18 amps of current, so a 20 amp range, and this equates to 100 millivolts per amp, which means if I set 10 amps per volt, so if I set a 2 volt range, that gives me a 20 amp span, which is what I want, and the conversion is straightforward. 4 amps, 8 amps, 12, 16, 20 amps. I don't really need to call it current. It means that I can very quickly then remove this clamp and replace it with a voltage probe if I wish, without any changes to the software. So it's a pure economic workshop way in which we operate. However, it does want zeroing. There's a slight deviation. So we push the 0 button. We've now set the 0 baseline at 0. That's ready to attach to an injector. In fact, we can attach it now. I don't know which way round this needs to go yet, so we may have to change that. I'm just going to take a guess as to which way around it goes. If the current is inverted down, of course, we want to reverse the clamp and get it in a positive direction. Right, the scope is set up. The first thing we could do is actually turn the key on without starting the engine, because we're going to see a couple of things which would be interesting and worthwhile monitoring. So you can key on, but don't start, please. Right, I'm using a short time base. Why? Because I want to see the actual control event. So what we're looking at there is the control event to the DRV. It is permanently fed with power and is ground switched through the computer. So ground is the on event, and you can see from that that it is more off than on, and roughly 75 off, 25 on. The correct duty for this vehicle running at idle is around 18% on from this valve with 1.3 volts from the rail pressure sensor, which equates to 300 bar. That's the balance I want to see. The actual rail pressure voltage in red should have a plausibility value, i.e. key on static as we are now, of 0.5 of a volt. I can measure it with the cursor or with the marker, and if I left mouse, channel B, red, 518 millivolts, that's near enough. So the plausibility voltage, static, is correct. Output power ground, therefore, must be correct. The next stage now is to increase this time base to provide enough time for us to go through this process of cranking, starting, etc. If I do that, and I want about 50 seconds, so if I change to 5 seconds per division with a 10 grid screen, that gives me 50 seconds. You can see now that those control events have been compressed into an envelope, and what we get is a broad band. So we can no longer actually use that to any value. So for now, I'm going to turn channel 1 off, and we'll come back to that later. So all we're interested in at the moment is looking at the voltage from the rail pressure sensor during this profile testing technique. So I'm just going to wait until it's passed across the screen. Unfortunately, when we use this screen, it denies me access to the keypad for stop and start. So we're just going to allow that to continue across the screen, and then we'll begin our test very shortly. As I say, we're going to do a whole series of tests, not just to see what the voltage is, but also how quickly the voltage changes in respect of cranking and starting and full throttle. So if you can get ready, if you could turn the key off to begin with, please. That's the system parked up. Key on, static, do not crank. There's your half volt. Crank and start, do not rev up. Full throttle. And off. There we have a full profile. I'm also waiting just to allow the decay to take place, and now the ECU is turned off. Okay. What we need to do now is review the data. The green image in the background is the current through the injectors. The clamp is the right way around. The current's going positive, which is good. I'm going to remove that part of the analysis for the moment and concentrate just on this rail pressure. We've established 0.5 of a volt, key on static, that's fine. I want to now look at this section here. This is a section where we crank and start the car. And in particular, I want to look at the rate of rise. I want to look at the value, that's voltage against pressure, and the rate of rise. What we should see is about 1.4 volts, which is a little bit too much. We're expecting 1.3, 300 bar, being brought under control by the ECU, and that looks as though that's being achieved. So the first thing is to measure the voltage, and then the rise time. This system should create 300 bar in well under 1 second of real time. So first of all, let's use the cursor. I'm going to take an average of that voltage event. 1.5 volts, so that's well over 300 bar. So there's nothing wrong with the pressure created during the cranking process. And now the rise time. So I'm going to use the vertical curtains, I should say. And I'm going to take a mean average also of when that pressure was achieved. 675 milliseconds, that's just under 0.7 of a second. That's excellent. There is nothing at all hydraulically wrong with this system. The priming system is working. The high pressure system is working. In fact, that wouldn't work if priming wasn't working. We know priming is working. We're monitoring that. There is nothing wrong with that. We now need to challenge this system on load, which is the acceleration test. So the next part of this assessment is to look at this part of the test. I want to look at the maximum value voltage achieved. This can vary from system to system, but this particular variation, Bosch CP1 DDE4, should create in excess of 4 volts peak voltage when the engine is revved up statically. So back to the horizontal cursor, I'm looking for a peak value somewhere around there. There's quite a bit of noise. Noise is actually created and caused by the injectors, and of course it compresses. So I'm going to take a mean average of that part of the signal, and it's 4.164, so it's well over 4 volts. It's a 1350 bar system, 4 volts out of 4.5. 4.5 volts is maximum pressure. We're well above 1000 bar pressure. So once again, the rate of rise is very aggressive. We're well over 1000 bar or around 1000 bar pressure. So hydraulically, there's nothing wrong with this system. That further challenges priming, of course, because the whole pump has to work harder. And the rate of rise, we'll take a plot, because this is now at 300 bar at idle. And I'm also going to take a mean average of the maximum pressure, and that's taken 1.5 seconds. There again, I'm quite happy with the results. I'm happy because of the profile. 1 second would be nice. It's a little bit over that, but I have no problems at all with the shape and profile of that. Equally, when we lift off, want to watch it smoothly achieve the 1.3 volts. And let's just check that it is 1.3 volts. So I'm moving the horizontal cursor down. 1.382, excellent. And you can see that when it was at idle, we then extended the full throttle test. It's returned perfectly back to 1.3 volts. That also means that this device, which has to close, dramatically close to achieve that pressure up, then has to, in effect, dramatically open to bring this voltage or pressure back under control. If this were sticking mechanically, you would have deviation. It would struggle to achieve that closed loop control. It hasn't. So back to the full image, and I'll remove the cursors because we've finished with that part of the measurement. So you can see from the overall view, stabilisation of pressure is good, crank start build up is good, full throttle is good. Decay can be assessed, the time it takes for the pressure in the rail to diminish back to 0.5, which is zero pressure. 0.5 does not represent a pressure at all, it is a zero. And you can see from that it's taken about 5-8 seconds or so of time to diminish. Bosch CP1's around 9.5 seconds. So I don't anticipate any internal leaks either. So really, what I'm saying is this system at the moment is perfect. There are no faults with this vehicle. Which, as frustrating as it is, this is the real life. The process is good. There's nothing wrong with process. We now have to wait till the fault actually demonstrates itself. However, we haven't looked at the injectors. That was a separate DTC, which potentially could be the cause. If you recall, what I said was, if an injector coil were to fail, or the ECU capacitor were to fail, then it will not drive the injectors, the vehicle will cut out and or not start. The capacitor voltage referred to is the voltage that you will read through a scan tool, 60 to 80 volts, ideally nearer the 80 volt mark. Remember the rule? current down, voltage up. We're measuring the induced voltage into the coil when the current path is interrupted. We're measuring current. That's the current path of the injectors, one injector. So if I slide the voltage up, I'm going to zoom into a very tight area. These injectors work on the principle of two events, pilot and main, which I'm going to zoom into in a moment. And this event here is an extra event which takes place to top up the capacitor in order that that capacitor is charged sufficiently to open the next injector event. Which is why, if one injector were to fail, that won't happen, therefore the next injector opening event will not happen. So let's just zoom in still further, and further again. Now we're now looking at pilot and the main fueling event. Current, which is a real event, in other words it takes into account by measuring current, we take into account power supply, which is the capacitor, and the ground reference through the ECU. We have 1.87 volts, that's 18.7 amps up at the top of the page, and we're making very close to that figure. So we're making above 18 amps of current flow. There is nothing wrong with the driver circuit to this injector, and therefore I am satisfied that the coil and the ECU and the wiring and the capacitor and the ground are all good. That's on that injector. We do of course have to then test each individual injector and or wait until a failure occurs to determine if one particular injector has failed. So I'm just referring back to the DTCs. It does say intermittent capacitor 1 voltage, so it's not actually detected a particular injector circuit, it's just said capacitor 1 voltage, booster voltage too low. What it's actually saying is not enough current flow through the injector. That could be a bad earth, it could be a bad power supply to the ECU, it could be somebody has just unplugged the injector and tried to start it, because there won't be any capacitor voltage, therefore it will be too low. So I'm happy with that. And you can see a whole range of, you can see the frequency changes. Well, obviously when you rev the vehicle up you get a much higher frequency. You can then see that on overrun, when you do not require fuel, the injectors are turned off and they come back on promptly to enable the vehicle to idle again. So there's nothing unusual there. And if we look at this little bit here, the other interesting fact is that this system will not start until 1 volt is achieved in the rail pressure sensor. And if we look at the rate of rise here and we look at the first injected event, I bring the two together, try and get this quite accurate. So the first injector event has took place at 1.176 volts. And you can see that the noise, there's an absence of noise here, no injectors. And the first injector noise spike occurs there, which is caused by the opening and closing of the injector. The high current flow occurred at 1.176. So the system is behaving impeccably. If you don't make 1 volt, it ain't going to go. So, analysis complete. There's nothing whatsoever wrong with this vehicle. The process is perfect in its construction. All we now have to do is to wait for whatever's wrong with this car to occur, and we're ready to monitor it. So quite simply, I'm going to have to discuss the options with the customer, continue testing until such time as the vehicle cuts out. I will attempt to find out if there's anything else that's perhaps relevant to the vehicle not starting. Temperature, hot weather, cold weather, moist, whatever. Does it happen static? Does it happen when the vehicle's driving? Does it happen after a period of driving? I need some more information now. I have all the technical information I require, all the measurements I need to establish what the cause is, not the symptoms. These are symptoms. I now need opportunity. An opportunity is a car to break down. So I hope this has been of some interest, and you see how we are intuitive about the tests we do, the process, procedure, and how we interpret these events, not being led by DTCs, but being led by the potential causes of these DTCs. And hopefully you can apply this principle to any form of diagnostic process. So I'd like to thank you for joining me, and I look forward to meeting you again in the next edition. Thank you very much.